Hi, my name is Jeff Neiman, and I will be talking today about a machine learning model that we actually went through the CRISP-DM process and put into production, and how we went through and solved the various systematic issues, how we adjusted for concept and data drift, and how we make sure that the model is performing as expected. So, the problem that we have is that supply chains over the last couple of years have made headlines not for necessarily good reasons. There's been massive supply disruptions to manufacturing and in turn consumer product industries. And because of that, manufacturers are essentially crippled in their ability to produce on time, as well as be able to produce to what consumer demand is. And that causes a lot of different issues. But today we're just focusing on how do we make the supply chain more robust. So there are many layers of a supply chain, but the one that people can actually really take action on is really going to be the first tier of the supply chain, right? And that's going to be who the manufacturer is buying parts or components from. The mechanism how goods are delivered, right, is a purchase order. So because we have open purchase order data, we have historical purchasing data that are going to have attributes like supplier, part number, whatever the widget is, when it was ordered, when it was delivered, right? There's a lot of different data features we can create that if we don't get these things delivered on time, they're in turn going to cause disruption to our manufacturing goods. The goal here is that we want to create a tool that's going to help ease manufacturing disruptions and improve supply chain performance. Because we have a large data set, both at a part and supplier level, this makes for a really good opportunity for machine learning. This isn't going to be something where the machine takes over completely, but this is more of a human in the loop with a machine learning prediction problem. So how are we going to measure success? Measuring success is going to be a twofold endeavor, right? We have a human in the loop that's going to give predictions that need to drive action. So the first and foremost, the most meaningful measurement of success is going to be essentially measuring the frequency and duration of manufacturing disruptions. And we want a baseline, and then we want to see what the manufacturing disruptions caused by late purchase orders are after we implement the model. This is going to be a really good measure of how we know if the predictions are actually being actioned, and that's really the goal, right? We want to make a machine learning model that gets actioned and leads to better supply chain performance. The second measure of success is going to be the model's overall performance, and that is going to be monitored with different statistical measures such as accuracy and precision. Because of humans in the loop, both the model and business performance are meaningful. If the model's performance are at or above the desired level, but the business outcomes have not shifted, the problem is not necessarily the model, but just in the delivery mechanism, the implementation, business process, and those other considerations. And those are important, but they need to be solutioned differently than just making a better model. To be successful, the model must fit within the daily user's work stream. Use of the user interface must allow the business to perform its tasks, and is going to assist what tasks to prioritize, and that's really the end goal of the model. Additional factors here is that we're going to create some KPIs for the business that we can actually show tangible success, and then we can gain buy-in from leadership. The model is delivering the results that the business cares about. So from a systems design standpoint, what we're going to do is we're going to use a cloud system. We're going to use offline learning and batch predictions. Ideally, the model is going to be able to predict if the purchase order is late, but also how late it is. But if the model can't do that, we're going to measure that with model performance. Then we'll shift to a classification model. And because of the human in the loop is going to be executing work daily, we want to look at the frequency of data that is getting generated. And really, the purchase orders are issued on kind of a weekly batch in this instance. So therefore, if we want to make new predictions over new purchase orders, we really only need to run the model itself once a week. This isn't necessarily training, this is just running over new data. And because of the frequency of new data and the amount of data we need to process, that's what's going to lead us to choose to a cloud system with offline learning. And we are going to make batch predictions. We don't need to do online predictions. We don't need to do online learning. And we definitely don't need edge computing here. So some risks here to the model. If we look at training serving skew, we don't expect there to be any skew because we're going to set up the pipelines and monitor those pipelines to make sure the data is populated before weekly POs are cut. Latency is going to be dealt with through monitoring, again, the data pipelines. So this is really about monitoring data quality, but we don't expect that to be an issue, and it has not been. Data drift and concept drift, this is really going to come down to monitor model performance. The elements that are really going to cause these are going to be things like new parts, new suppliers, new things, or like events that are going to cause massive declines in supplier performance. So if we see model performance dip below percentage, and we'll get that percentage from the business, then at that point we'll set the model to retrain. So this is the past due prediction model. Thank you for listening, and that is all.